So some classes in Chem 1 don't get to this chapter, and some do. Now, officially on our syllabus, we start Chem 2 here with solutions. So some of you might have already seen it. Some of you don't remember it because it's been too long. Some of your teachers barely finished Vesper. So it really depends on where your Chem 1 background was, but to get us all up back to base, I'm starting here. And if you needed to look at old material, I also have some extra old material posted for you guys, okay? So the solutions chapter, so what in the world is a solution? What do you guys think of when I say solution? So what is a solution? So if you think of a solution, all you guys most of the time is you're just saying, well, solutions are just, well, like if you go to lab, you make a solution, it's usually a beaker of water or a flask. And then you put some solids in it and you stir it up, you make a solution, correct? So that's a traditional solution you think of when you want to say, well, I want to talk about a solution. Now, technically, a real definition of solution is anything that is a homogeneous mixture. So what in the world is a homogeneous mixture? Do you guys remember we learned homogeneous mixture way back in Chem 1 a long time ago, where we learned about pure substance and then we have mixtures. Now under pure substance and mixtures, the mixture part, you have two types. We have homogeneous and heterogeneous. So heterogeneous is the one that's not mixed evenly. Homogeneous is the one where it's mixed evenly. So anything that is mixed evenly can be considered a solution. So that really broadens up our definition of a solution, okay? We will only focus on a few different kinds of solutions here. But basically, under the solution here, we have solute and we have solvent. So when you have a solute and a solvent, you have to decide who's the solute and who's the solvent. Well, an easy way to think about it is the thing that changes its phase. So if you put some sugar in water, the sugar changes phase to aqueous, right? So the thing that changes phase is the solute. The thing that doesn't change the phase, like you put sugar in water, water stays liquid, well then water is considered a solvent. So that's an easy way to think about things, okay? The thing that changes phase is the solute, the thing that doesn't change phase is the solvent. Now, if both parts of them are the same state, like if both are liquid. So an example of liquid and liquid is like vodka. If you have ethanol and water mixed together, well, how do you tell who's solid and solvent? Because they're both still in the aqueous liquid form, right? So the bigger component will be the solvent, the smaller component. Like you can take a look at mole ratio, the smaller component will be considered a solute, okay? So that's one thing. I'm going to talk about mixtures. So we have different kinds of solutions here. So the one that we are really familiar with is solid and liquid. So solid dissolving in liquid like seawater, or we can say sugar water, or even like tea or whatever, anything that's homogeneously evenly mixed. Okay, gaseous solution is gas and gas. An easy example is our atmosphere and the air. I mean, you hope our gas, like if you stand in a room, one corner of the room has the same exact amount of ratios of the oxygen and nitrogen, whatever, as the other corner of the room. If it wasn't, we'd be in trouble, right? You could walk to one side of the room and just suffocate because you can't breathe. Well, I guess that could happen if you have carbon monoxide poisoning. But that's different. We're just talking about air, not extra material. So that's gaseous solution. Now liquid solution, you have gas and liquid. So this thing, sometimes we don't think about it, but like your carbonation in your drinks, that's a form of solution. Okay, we will talk a little bit about this. We want to talk about solubility of gas in liquid, basically. Anytime you put gas in there, how much, well, how to calculate the solubility, what does it depend on? We'll talk about that. So that will be like your carbonated drinks, your soda. Liquid and liquid, we just mentioned that. That's like vodka, where you mix ethanol and water. So basically, if they're both the same liquid phase, that's another solution. The common one that we will focus a lot on is solid and liquid. So we will be doing a lot of stuff with these guys, this category, okay? Now, solid solution, solid and solid here, you can use like basically alloys or brass, example, copper and zinc mixture. We don't do too much on the gaseous solution and solid solution, but it's a good thing to know that, hey, you know, our salt solutions are actually anything that's a homogeneous mixture. It's not just putting salt in water or putting sugar in water, okay? Now, we just want to talk about what is solubility. Obviously, when we want to calculate solubility, how do you define something as soluble? Something that goes into and dissolves into the solvent is considered soluble. When something doesn't want to dissolve, it will be considered insoluble. So the ability for it to mix depends on two things. This nature's tendency toward mixing is basically the entropy part, where if you put two things separated and they were separated by some divider and you lifted the divider up, automatically they're gonna wanna mix. So that's the nature tendency toward mixing. That's how one factor that helps solution form. And then also it depends on the intermolecular forces. So if we learn intermolecular forces in Chem 1, we have different types, right? Like, you know, we have dipole-dipole, we have London dispersion, we have hydrogen bonding, ion dipole. These things help the molecules attract to each other, and they can help contribute to the solution forming. And in this part here is the entropy, where if you have two separate things, you lifted it up, they want it to mix. So these are the two factors that make solutions possible, okay? So the steps to make a solution, there's a few steps. If you guys have questions anytime, just make sure you, I am looking at the chat so I can see it, or use your space bar and ask questions, okay? Over here, what you wanna do when you make a solution, so if you wanna make a solution, it has to be a homogeneous mixture, correct? It has to be a homogeneous mixture. First, you have two separate things. You have the solute on one side, you have the solvent on one side, okay? So when you have solute and solvent on one side, you have to sort of get them ready to mix. To get them ready to mix, number one, you must take the solute and the solute interaction. You must kind of like, okay guys, you kind of have to separate. I know you like to be with each other, but you want to separate a little bit so you can get ready to mix with something else. So you have to overcome that solution, that solute-solute interaction, okay? And then you do the same with the solvent, overcome those interaction, and then you say, hey guys, why don't you meet and be new friends? That's the combination part where the solute and solvent interaction comes into place, okay? So just making sure you know there's energetics here as well when you want to do making solutions. So if you think about it, when we learn in thermodynamics in Chem 1, if you break a bond apart, you have to, like say if this is a bond here and I'm trying to break it, it's technically not a bond for solution because it's intermolecular forces, but it's still something to overcome, right? To overcome any connection force, you have to put in energy. So this causes a positive energy here. So this is going to be endothermic process to overcome solute and solute. And the solvent and solvent is also endothermic because you need energy, you need some sort of force to kind of help them separate. Now, after you separate them, these all take in energy. The connection between the solute and the solvent is kind of like, oh, I really like you, and they form a connection there. That connection, depending on how strong it is, it releases a lot of energy. So it's an exothermic process here when they combine together. So depending on how exothermic is, you can see if a solution will form or cannot form. Okay, so that's what this table is telling you. Like if your energy levels, so I'm going to show you a picture here, hold on. Right here on this slide. Okay, so you see how you separate the solid, it goes up in energy. You separate the solvent, it goes up in energy. Now you're way up, you're like, okay, well, I just spent all this energy to separate these guys. They're separated. Now when you form, it releases a lot of energy. You form a solution. So if you form a solution and it really, really likes each other, it's really exothermic. Your net process is exothermic. So it's favorable for a solution to form, okay? Now, if you had a case where you put separate, and then you tie up here, and then they form a solution, but they didn't really like that much, it doesn't go out that much, but it's a little bit positive. The net is still a little bit positive. A solution can still possibly form here because of the mixing factor. Now, if this is way, way, way up here, then the mixing factor might not be able to help and you still will not form a solution. So that's what they're talking about when there's energetics for it, okay? So we won't do too much calculation on it, so don't worry about that. But I do want to talk about things that can mix and things cannot mix. So solubility, we know like oil and water can't mix, so those are immiscible. Alcohol, water mixes, so they're miscible. It's because they're attracted to each other. So it's like polar and polar, non-polar, non-polar, okay? And then we also talk about solubility, how much solid you can take. So we'll go on to the next slides for a little bit here. Light dissolves light. So we want to talk about polarity, okay? So polar stuff, hopefully you remember, is where the electronegativity difference between the two atoms or overall in a molecule is pretty different. Like one side is sort of the positive end and the other side is sort of the negative end. So they have some sort of polarity in the structure, okay? Polar stuff attracts another polar item. And when a polar and polar come up next to each other, they actually line up where their plus and minus all kind of line up together, okay? So common polar solvents, we have water, acetone, all the alcohols that you know of, they're all polar as well. Why? Because the OH group is extremely polar and they're small, so the OH is really a big deal there. When it becomes a big, big, big molecule, the OH sometimes is not that big of an impact. Now, common non-polar solvents are hexane. These are actually used a lot in lab. It's just a 6-carbon straight chain. And you have hydrogen sticking out of the carbon. Each carbon will have 4 groups. So if the carbon is next to another carbon, they will have 3 hydrogens stuck on it. And if carbon is stuck between 2 carbons, you will have 2 more hydrogens on top of it. So hopefully you remember what that looks like. If we're not, we can talk about it after class as well. These are examples here. You don't need to worry too much about that. Now, vitamins here, we have fat soluble and water soluble vitamins, agree? So over here, we can take a look and see some of the vitamins here. Some of them are fat soluble and water soluble. How can we predict? Well, look for polar molecules all over it, polar groups. See how vitamin C, CO, that's polar group. That's another polar group. That's another polar group. That's kind of polar, C and O, right? OH and OH, that's really polar all around. So something that's polar all around like this will make it water soluble, okay? Now, take a look at this guy, vitamin K3. CO and CO, but that's it. Everybody else is CH and CH. CC and CH are non-polar, remember that, okay? Anything that's nitrogen, oxygen, and fluorine bonded to a carbon or oxygen, those guys, those are polar, but CC, CH, those are non-polar. So you see how CCCH all over here? Those are non-polar. So in the CO and CO, they're sort of opposite sides. They sort of cancel each other out. So vitamin K3 is actually fat soluble here. Okay, now let's take a look at vitamin A. So vitamin A here, if you take a look, everybody is CH, CC, CH all over here. And then there's one little corner that's OH. This one little corner, OH here, is not enough to make it dissolve in water. So this will be fat soluble here because it's one small polar side compared to the whole big gigantic non-polar. So this guy here is fat soluble. Okay, now take a look at vitamin B5. You got CO, OH. So see how polar group, and then there's NH, another polar group here, and then OH and OH. See how there's all over around it? So this is an indication that this one here will be water soluble, okay?
So wait, with vitamin A, where it's just the OH on the end, is it going to be apparently obvious when that's not really going to affect the...
Yeah, when the molecule is really, really big and you have only one small spot, it's not enough to make it go in.
Okay, so it's common to see that, sort of?
Yeah.
Okay, thank you.
All right, so it's kind of cool. So, you know, when you guys drink like the vitamin water, you know how like drinks have vitamins in there? I always wonder, are those all, I never really look because I don't really drink them. But like, have you ever considered looking at the labels and see what vitamins are included in there? Are they all water soluble? If they're not water soluble, how are they keeping it soluble in your water? You ever thought about that? Like, so maybe if you have a bottle of vitamin water, take a look at it and see what kind of vitamins are on there. Is it water soluble? If it's not water soluble, how are they keeping it in your water? So here's the funny thing, like if you drink like soda, there's food coloring in there. There are some drinks, obviously we have regulations here and some things, molecules are banned. I have a long time ago grabbed a bottle of soda. It was like a thing from Jamaica, because I think I was in the Caribbean restaurant, and I read the label on there. There's this food coloring, and it's a non-polar molecule, and they have it dispersed in a drink that's clearly full of water. How did they do that? They use a molecule that ties these together. So this extra coloring, first of all, you don't need the coloring. And to make the color stay in a solution, they had to use another chemical to tie it together. Like I think it was brominated vegetable oil, and I believe that's banned here. But it was in your drink. It was kind of crazy. You see, like people want to use food coloring, and they use like propylene glycol to put it in your food. You'll be surprised when you read labels. Okay, so just FYI, read your labels, and you'll be surprised at what you learn. All right, so here's another question here. They're asking you if it's going to be soluble or not in water or in hexane. So hexane is nonpolar because it's C and H. You see how CH, CH, CC, those are all nonpolar. Water is polar here. So naphthalene here, if you take a look, it's all CCCH. And that's why we know it's nonpolar. It will go in hexane. Okay, now here's a small molecule here, and there's a CO. So when it's a small molecule and you have one polar group, it will be polar, it will go in water. But if you have a gigantic long thing here, right? You see this long thing, all CCCH? And then there's one little N here, okay? This is going to be soluble in hexane, okay? Not so much in water. Now, the cool thing about stearic acid is it's actually one of the components you find in olive oil. Olive oil, majority of component is similar to this, except on the 10th carbon. So you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. On this carbon here, instead of a single bond, there is a double bond here for that guy. So this is stearic acid. The guy with the double bond is called oleic acid, and it makes a double bond so it it's not a straight chain, it kinks, it kind of bends a little bit. But that's a major component of olive oil. So it's kind of cool that you see this and you actually consume this. So we don't want to consume that, okay? Formaldehyde, it's not that great. All right, so let's take a look here. We talked about that. We don't need to worry about the heat to hydration stuff. You guys do remember ion-dipole interaction here? Whenever we have an ionic compound and we put it in water, the ion-dipole interaction shows you that the positive cation here is connected, is aligned really nicely with all the negative ends of your water. So the negative end is attracted to the positive ion, and the positive end of water is attracted to the negative anion here. So this here is a picture of the ion-dipole interaction. And it's gonna be a big part because we're gonna do a lot of like ionic solution calculations, okay? All right, so let's talk about the next thing here. So over here, we have NaCl when you try to dissolve it. So in here, when you visually look at things, so when you first put a clump of salt in your water, what's actually happening? The salt's like, woohoo, I can dissolve, and they all go crazy dissolving, okay? But what they don't tell you is there's actually at the same time, a few of them are turning back into NaCl. So every time you dissolve, in the beginning, a whole lot of dissolution is happening, and then some of it is recrystallizing back. It's actually a reversible process. They don't mention it, but there is a back and forth going on. over time, once it reaches to a point, you know how when you put in more and more salt, at some point it just stops going in, it hits the saturation level, and you see some salt left over out there. It's because at that point here, and it looks like it's not going to change anymore. It's because the rate of this dissolution has slowed down, and the rate of recrystallization picked up a little bit to the point where these two are now equal opposite rates. Okay, so at first it will want to dissolve a whole lot, very little bit of recrystallization. And once you feel like there's a lot of dissolved stuff all over the water, they're like, you know, it's kind of getting a little crowded. You guys should think about going back to being a compound together. So they recrystallize back. So over time, this slows down, this one picks up speed, and this becomes the same speed. When these two are the same speed here, we call this a dynamic equilibrium, and this will be the concept for all of chapters 16, 17, and 18, where there's two processes happening in opposites and equal opposite rates. We will have something we call dynamic equilibrium. So here's just a small introduction to it. We won't really be doing much with it yet, but just want to know that this will be the focus on our next exam topics. Okay, so with the solubility limit, so when you hit a point where it won't go anymore, it took as much as it can, we call it saturated. Okay, now something that you can still take more is unsaturated, something that is holding more than it should is called supersaturated. Now, how do you get something to be supersaturated state? We know we can get it to saturation. We know unsaturated. How do you get it to supersaturated? Have you guys thought about that? Anyone try to make crystals before? Like at home crystal kits, like home making kits? Yeah, so you could totally do this at home if you wanted to make a supersaturated solution. Supersaturated solution is a source of crystals. It's actually a really cool and simple purification technique. So what you do is you get something to become supersaturated. How I'll tell you in a little bit. Once something is supersaturated, any disturbance of it will cause, like you just touch it, it causes a seed of the crystal to form. And when there's one seed, all the other guys grow on that seed, and it starts to, if you don't mess with it, it will start to grow really long, pretty crystals. The longer you go, the more crystals will form, and only the pure stuff will come out as crystals. So when you get to this point, what people do is you filter it. So essentially, you just clean your crystals away from the impurities. So this is a really common method of purification. Okay, so how do we get something to go to supersaturation level? You trick it. So how do we trick it? Everyone heard of rock candy before? Okay, so how do you make rock candy? To make rock candy, we actually will have to have a pot of water, right? And a whole ton of sugar. I don't know how much sugar, but you keep putting sugar in. So what do people do when you're trying to put sugar into the water? You actually heat it up, right? So one thing we notice is when the temperature goes up, okay? So here's a graph here. It looks, so ignore this outlier. But you see how everybody's going up like this? So this is solubility, okay? Going up as you increase temperature. If temperature goes up, solubility goes up. So you see how everybody's curving up that way, except for this guy. Don't look at that guy. Every time there's a trend, there's always one or two outliers. But they're saying, if you increase the temperature, the stuff will dissolve better. More stuff will dissolve. Agree? If you wanted to put sugar in cold water, it's not gonna go, but you had it in hot water, it will go quickly. It will go easily because it can take a lot of sugar. So with increasing temperature, you increase solubility. So what you do is you take sugar, you put it in cold water, and you're like, oh, it's not going, it's saturated at cold. Turn the heat up, put more sugar, and it takes more. You trick it to take more by increasing the heat, and then at some point, you put a whole lot of sugar because it's so super hot, and then you turn the heat off. When you turn the heat off, what happens? The sugar was already in the solution, but you turn the heat off, and then the solution's like, hold on a second, I was really happy. It's kind of like the frog in the hot water, slowly heating water analogy, I guess. Over time, the frog doesn't realize you're heating it up, so it thinks like it's taking a hot bath, and then you cooked it by the end. So this is kind of the trick you do to make something super saturated. You heat it, and it will keep taking more as long as you keep heating it. The hotter it is, the more sugar it can take. And then when you turn off the heat, the solution cools down. And the solution's like, hold on a second. I was just at saturation level when I was hot, but now I'm cold, so I'm super saturated. So it becomes where it was tricked to take in more than it's supposed to. So that's what a supersaturated solution is. And then you put your sticks in there and you can form crystals. So the rock candies are actually crystals. You can do crystal solutions of sugar. You can make crystals that way. You can use salt. You can use different kinds of salt and make different kinds of crystals that way. So that's what we wanted to talk about for recrystallization of solid. Now, the next part here, I will do the math the next class, probably it's Henry's law, but I wanted you guys to take a look at this picture here. So earlier we were talking about heating solid up, heating the liquid up to make sure the solution take more solid to make it super saturated. But what about something that's warm? Would heating of a solution increase the solubility of the gas in the water? Because we say we heat it up, it will take more sugar, it would take more solid. But if you did it with gas, it will actually be the opposite. If you had a solution of gas in water, if you increase the temperature, the solubility of gas actually decreases. Because if it's warm, a lot of gas will try to fizz out, it will leave the solution. If it's cold, the gas is able to stay in your solution better. So when you drink the cold one, it's still fizzy, right? This one's flat because all the gas left because it's warm. Okay, so this is temperature dependence of solubility of gas. So make sure you know that. So we just talked about solid. If you increase the temperature, it dissolves better in liquid. If you increase the temperature for gas, it will actually do the opposite. Okay? So the last time we were in class, we talked about basically solubility of stuff. We talked about how the vitamins can be fat or water soluble, right? Because polar and polar, non-polar and non-polar. And then we started talking about solutions. If you wanted to make something super saturated or make it to saturation, you would have to take your temperature, like your liquid, and you have to raise the temperature so the solid can dissolve better. So like to make rock candy, you make it super saturated by heating up the water really, really high temperature, and to encourage it to dissolve up to the saturation at the higher level. Because as you can see in this graph before this picture here, it shows you, let's say, for example here, this green line here, if it's at 10 degrees Celsius, it dissolves at 20 grams per 100 grams of water. If you raise it up to like 50, you can dissolve 50 degrees Celsius, you can dissolve 90 grams of the solute in 100 grams of solution. So basically it tells you you can really increase solubility of solid when you raise the temperature. And that's how you can trick a solution to be super saturated. Raising the temperature up really high so it takes on one that's at this level, at this high solubility level, and then all of a sudden you trick it. You're like, okay, turn off the heat, and it cools down to room temperature where it already has 90 in it, but at room temperature, it's only supposed to have about 30. So that's how you can tell it's super saturated. When something is super saturated, you touch it, make a seed, crystals grow. This is a very, very basic purification technique that you will use when you go to organic chemistry as well, okay? So the next thing we talked about was if you wanted to do the gas in water, what happens is actually the opposite. If you heated up the water, the gas is less likely to stay soluble. Increasing temperature of the liquid actually reduces the solubility of gas. So if you take a look, as you increase the temperature, the solubility of the gas, it drops, right? The number gets smaller. So that's just showing you here a trend here. This one here at 0 Celsius, it starts at 89.5 grams of ammonia per 100 grams of water. And if you raise up the temperature really high, it drops it down to 3 grams. Okay, so basically, if you don't have to worry about the chart, but if you take a look at this picture, you kind of remember if the soda is warm, the gas will come out a lot faster and it will be flat before you know it. But when it's cold, the gas can stay in solution longer and it will give you that fizzy and that you like when you drink. I actually don't like the fizziness. It makes my throat feels weird. I don't know about you guys. But anyway, so that was about temperature, right? So what about pressure? So you guys ever thought about pressure? Like when you open a new can of drink, right? When you open, you hear like a pressure is being released, like as if inside the can was higher pressure. And it really is higher pressure because the higher the pressure, the higher the solubility of gas. Okay, and that brings us to Henry's law, which basically says the solubility of gas is related to exactly proportionate with a constant to the pressure of the gas. So just think about this. If you have original state here, this is at equilibrium. Equilibrium means it's happy the way it is. It's already gone through the changes, and the rate of going out into gas and rate of turning back into liquid is the same, okay? Now, all you do is if you push it to make it smaller space, the smaller volume makes it increase in pressure. Increasing the pressure will be like, the gas will be like, hold on a second, we were right here, all of us were really happy in this space, and now there's very little space here. So what happens is the gas will be like, you know what, some of you guys better turn into liquid phase so we don't have to be so cramped up here. That's why you have to increase pressure to increase solubility of gas. Okay, if you release the pressure, then basically they have more space and the gas will try to come out as gas form instead of being soluble in a liquid. Okay, so let's take a look at Henry's law. It says here, Henry's law is solubility of the gas, which we will use in units of some concentration. In our case, most of the time will be molarity. So solubility will be units of molarity equals to Kh. This Kh here is Henry's law's constant. Okay, now every gas will have different constant at different temperature. So I do not expect you to memorize this. You will be given the value that you need. Now, if you're doing homework, they don't give you that actual value. If you can't see, let me zoom in a little bit for you guys so you don't have to squint too hard. This Kh here, you don't have to memorize, but it will be provided. On homework, you'll have to click on the link on the top to pull up some tables of constants there sometimes, okay? And then Kh times partial pressure of that gas alone. So partial pressure of that gas is just simply gas contributed by that gas that you're talking about, okay? So if you have a mixture of gas, you want to focus on the gas that you're interested in. Say maybe you have O2 and N2 mixed together. Maybe they ask for just O2, then you focus on the pressure of O2 and the molarity of the O2, okay? So here are the constants that are given. So let's go ahead and try our problem with Henry's law, okay? Now you'll see when you do your homework, there will be a few different kinds of Henry's law's problem. You'll have to remember what partial pressure looks like and stuff like that. So if you don't remember, make sure you do a little bit of review about how to do pressure calculations and molarity calculation, okay? So I'm gonna go ahead and write the question out for you guys. It says, so this is Henry's law. So what pressure of carbon dioxide is required to keep carbon dioxide concentration in a bottle of club soda? So does club soda have a taste? I've never actually had it. Is it just like fizziness, or does it?
Yeah, I'm pretty sure that's what it is. I don't think it has a taste at all, like from the last time I remembered.
Yeah, so it's probably just taste of like carbon dioxide, maybe a little bit sour from the carbonic acid. So club soda, at the molarity of club soda is 0.12 molarity at 25 degrees Celsius. So they gave us a temperature. So when you get the temperature, you look it up from a chart, or if it's a question that I write on a test or a quiz, I will make sure to put this in with you. So the Kh for carbon dioxide at this temperature here, okay, at 25 degrees Celsius, will be 3.4 times 10 to the minus 2, and the units will be in molarity per ATM. So if you remember from Chem 1, we learned pressure, and then we had a few different different units. So some of it was torr, ATM, millimeters mercury, right? So I need you to remember the conversion between these units. You guys remember what the conversion, obviously we don't need it in this problem, but you will see them coming up a lot, okay? So just to give you a refresher, 1 ATM is going to be 760 millimeters mercury, and it's also 760 torr. Okay, if you remember this, you should be good. There's one that might be helpful. This one is 76 centimeters mercury. Okay, so that's something you learn from Chem 1, but if you forgot about it, it's there right there. And you can always look in the gas chapter from Chem 1 notes if you guys are interested in learning more. Okay, so let's get back to this. So the Henry's Law's equation was solubility of carbon dioxide equals to the KH of carbon dioxide times the pressure of carbon dioxide. So all you do is you just fill in the blanks, okay? So what did they provide with us? They gave us the solubility, which goes here. They gave us that, it goes there. All you do is solve for pressure. Well, that makes it really easy. Okay, this is a very straightforward question. We always start with a simple concept question and then we build on top of it. So when you do your homework and do your dynamic study modules, okay? So let's put this here. I like to always write down my units. The reason why is because there's going to be, now remember molarity is capital M, okay? If you write little m, it means another unit. It's not molarity. And moles, please write MOL, okay? Don't write M because M stands for many things. It could be meter, and it could be molality, which we will learn if you haven't already. So it's just many different things that it could be. So don't use the little m, capital M as molarity, okay? And what is the unit for molarity, in case you guys forgot? It's moles per liters of solution, okay? All right, so let's put this in. So 3.4 times 10 to the minus 2 molarity per ATM. And then we can solve for P of CO2. So
I have a question.
Yes.
What does KH mean?
KH is Henry's Law's constant.
Constant.
Okay, so from the equation from our notes here, you see this little thing here? That's the KH.
Yes.
And that's the constant, okay? So sometimes the question will ask you to solve for pressure. Sometimes they'll ask you to solve for solubility. Sometimes they'll ask you to solve for the KH. So you just need to know where the equation, how it's written, and then you can solve for the missing piece. Okay, sometimes they'll give you a mixture of gases and ask you to solve for the one part of it and give you like the mole ratio with the total gas and tell you to solve for the pressure that way. You can do stuff like that, and that's all Chem 1 material. So I just want to make sure you do remember how to do that. When you see those problems on your homework and stuff, you'll start to recognize it, okay? Okay, yeah, if you can't hear anything, definitely try to see if you can raise the volume up to the max. Sometimes you guys are not connected on audio, but you should be able to if you guys just try to reconnect. Okay, so let's solve for the pressure here. So basically the pressure is 0.12 divided by 3.4 10 to the minus 2, okay? So hopefully you know how to do this on your calculator. And you just make sure you put 0.12 divided by, when you do this number, you can do a bracket around it when you type it in your calculator. And you end up, if you want to keep 2 sig figs, because we do have 2 sig figs on both places here, you ended up with 3.5 ATM. Okay, why ATM? Because molarity divided by molarity crosses off and the ATM on the bottom comes back up because it's divided. Do you guys see that? So I did not write the algebra out, but hopefully you guys follow that. Everyone good with that? Let me know if you have questions, okay? Now, so I wanted to show you guys now the next thing when I was talking about this molality here. This is actually a different unit of concentration that is pretty similar to molarity. So you have to make a distinction, capital M versus a lowercase m, okay? So let's take a look at different kinds of concentration solution. So this is stuff, most of this you already learned in Chem 1, but I wanted to put it all together and let's do a recap, and then we're gonna do conversions back and forth for different kinds of units here, okay? So first of all, one thing I want you to notice on this whole entire table is what's on the bottom, what is divided by, okay? On molarity is divided by volume of solution, right, in liters. Now, on mole fraction, solute and solvent is on the bottom, which equals to the solution. So the solute plus solvent is solution, okay? Mole percent, solute solvent, parts by mass, solution. Everybody's solution on the bottom. You guys see that? Who is not solution on the bottom? Molality is not the solution on the bottom. It is just the solvent. This is very important, okay? Because if you put the solution in there, you got it wrong. You have to put just the solvent on the bottom. And what unit of solvent are they using? They want kilograms of the solvent. So you have to make that distinction. This little m and the big M here is basically, this guy is the only guy that has just a solvent on the bottom, okay? So that helps you memorize the units if you can't remember which is which. Everybody else is all on the bottom, solution. The only thing that's not solution on the bottom is molality, where the solvent is on the bottom, okay? So let's take a look. Molarity is moles per liter. Moles of solute over liters of solution. Molality is moles of solute over kilograms of the solvent, not solution, okay? So that's what, it's just a different way to express concentration. Now, mole fraction is in moles, moles of what you're interested in over moles of everybody, which is moles of the solute on the top, moles of everybody is the total of solution. So you take the moles of solute plus the solvent on the bottom. If you take the mole fraction term, you multiply it by 100, you get mole percent. Okay, and then you can do the same with parts by mass, but instead of using moles here, you change it to mass in grams here. So mass of solute over mass of solution times whatever factor. If you want percent mass, which you guys do a lot when you do empirical formula calculations, so you have mass percent, you times 100. If you want ppm, you times a million, 10 to the power of 6. You want ppb times a billion, you get 10 to the power of 9 here. Okay, and you do the same if you want it parts by volume. You take volume of the solute over volume of the solution times 100 for percent, 10 to the power of 6 for ppm, 10 to the power of 9 for ppb. What they mostly ask is just a few stuff here. Parts per volume is not that common. Okay, so I want to go ahead and let's try some questions that involve these kind of solution calculations, okay? So if you needed to take a look at this again, this is on slide number 32 on your notes, okay? So you should be able to have this, and if you want, if you haven't already memorized this, go ahead and write it down and start to memorize which is which, okay? So let's go ahead and start with another question here. All right, it says here, what volume in milliliters of a soft drink that is 10.5% sucrose, and the formula for sucrose, let me write it out, is C12H22O11. And this percent mass sucrose is by mass. Okay, and so what volume of the soft drink that has this by mass contains 78.5 grams of sucrose? The density of the solution is, let me write it. 1.04 grams per mil. Okay, so you're like, okay, well, there's a question, how do I do this? So a lot of times when you guys see math questions, it's kind of hard to like kind of know what to do with stuff unless you've practiced and seen this kind of questions before, okay? So it's very important to be practicing. What I like to do is when I suggest you to have a good study habit is basically, number one, after class, a few hours later, I want you to rework all the problems I do in class. So as you do the notes, you write along with me, you're learning with me, but I want you to redo it a few hours later, see if you can do it on your own. Because if you can't, you don't have it filed in your long-term memory yet. You want to do it until you can, okay? And then definitely do your homework, do the extra credit. That solidifies your understanding of this concept. So how in the world do you do this? So what I have here is basically, I know it's 10.5% sucrose by mass. And I know that I want to get 78.5 grams of sucrose, and I know the density, okay? I am looking for milliliters. So you wanna go from basically 10.5 grams of sucrose, and you wanna go from the grams all the way to milliliters. Okay, how do you do that? Well, we have density here, so that's good, right? You can probably use that somewhere. And when you see density, I like to write it out like this. If you see density of 1.4 grams per liter, you can literally write, it means 1.4 grams of solution can be found in exactly, this is an exact number, it's unlimited sig fix, exactly 1 milliliter of solution. That is what density means. Okay, so you can use this for conversion later on. Now, another cool conversion here that you can use is this guy. It says 10.5% sucrose by mass. That means percent-wise, if you have 100% as a solution, 10.5 grams, 10.5 solution percent is the sucrose. So let's say if I say I had 100 grams of the solution, because this is an intrinsic property, it doesn't matter how much you have, so I like to pick a convenient unit. Like the density is also intrinsic, so I pick a convenient unit. I pick, well, you can pick whatever volume you want. You could have picked 100, 2,000, but 1 mil is easy because you can copy the number of the grams over here. So what I like to do is pick 100 grams of solution, because then I can copy 10.5 grams of sucrose over here. So based on that, I told you 10.5 grams of sucrose is found in 100 grams of solution. This 100 here is exact. And then 1.04 grams of solution can be found in 1 mil of the solution. So that gives us a few things to know how to convert. So remember, you're trying to go from 78.5 grams of sucrose, and you somehow have to go all the way to milliliter of the solution. That's what the question is asking. So now you start to see the pieces that you can put together. I see I can relate grams of sucrose to grams of solution, and then I can take grams of solution, link it to milliliters of solution. You guys see how we can connect those pieces now? So that's how you can set up your conversion there. So 78.5 grams of sucrose. Now, I get lazy to write the times 1 over times 1 over whatever, so I just start drawing a line here. But you can do it however you like, okay? So what's on top, I multiply. What's on the bottom, I divide. So what I want to do is get rid of the grams of sucrose. So I want to put the grams of sucrose on the bottom. So, and I want to convert it to grams of solution on the top here, so that goes on the top. Now then I just copy the numbers down. So 10.5 grams of sucrose goes on the bottom, 100 grams of solution goes on the top. I'm going pretty slow here because some of us here haven't taken Chem 1 in a long time. Hopefully you guys are okay with that. Yes, 719, it's perfect. That's the answer. I'm gonna work our way there. Sorry, we're a little slow. Some of us are still trying to wake up because most of us don't eat breakfast apparently. And then we want to convert to milliliters. So 1 milliliter of solution is on the top, and we want to get it grams of solution. So we go 1.04 grams of solution on the bottom. Okay, so you see how I like to write my number and then my unit so I can know it cancels out. See that grams of sucrose cancel with grams of sucrose? That you can cross off, and then that one can cross off with that. Okay, now in the end here with 3 sig figs, you do get 719 milliliters of solution. Now, my challenge question for this one here is based on this question. After you do all this stuff, here's a different question. I can twist it. I can say find molarity of this solution. Okay, the solution that was up here, which is, what was it? 10.5 by mass sucrose. So I'm gonna go ahead and give you the molar mass of sucrose. So molecular weight is, well, I just like MW for molar mass, okay? So molar mass of sucrose, C12. Each 22,011, that equals to 342.3 grams per mole. So if you wanted to do this, there's a few things you can, there's 2 ways you could have done this. But the easiest way, since we already did this previous question, is basically you need to somehow get, what's the unit of molarity again? It's moles of solute over liter of solution. You have to somehow get the moles of solute on the top and the liters of solution on the bottom. You already have this setup here. You know 719 mils of solution contains 78.5 grams of sucrose. You also know you have 100 grams of solution and 110.5 grams of sucrose. You have those parts. So you have 2 options. You could take this solution here, convert it to liters of solution by using the density of the solution and then turn it to liters. You could have done that. And then you take grams of sucrose divided by the molar mass to get the moles. But we already did this part. So we already did this one here, which we already got the mils, and we can easily convert this to liters, correct? This and this is a ratio here, and that's a ratio, but that one needed a little bit extra work here. So I'm gonna choose this option. Okay, but if I didn't give you this, you could have still done it with just that problem. That alone, you can do your molarity, okay? Because grams can be converted to milliliters of solution and then converted to liters. So not a lot of extra work. So over here, you take 78.5 grams of sucrose, somehow turn that into moles. So we're gonna take 78.5 grams of sucrose, turn it to moles of sucrose. And then 719, we'll just convert it to liters, right? Which is just divide by 1,000. This is liter of solution. So let's go ahead and do the moles and then the liter part. So 78.5 grams of sucrose. You just basically want to divide it by the molar mass because 1 mole of sucrose weighs 342.3 grams. So I'm going to get 0.229 moles of sucrose on the top here. And then the liters here, I'm just going to go ahead, if you divide it by 1,000, what is that? 719 divided by 1,000 is 0.719 liter. Okay, so you got the top and the bottom. So when you do your molarity, I'm running out of space on my paper, sorry. I'm gonna go here. It's 0.229 moles of my sucrose divided by 0.719 liters of the solution. And you will get 0.319 molarity. 319.319, okay? Yeah, I might have a small error here and there, but that's why we're learning here, we're practicing. So, you know, if you already knew all this stuff, you wouldn't be in this class. You'd be in another class. So, all right. So hopefully everyone followed the way we did this. And then we're gonna go and do some more molarity calculation and converting units. Hopefully you guys finish writing that. Before we do that, I'm gonna go ahead and write this question out. I wanna do a poll with you guys. So let's see. Launch poll. The poll is basically, I plan to use what kind of resources available to me to learn. I think you can select multiple choices on here. So our options here for learning resources is just kind of like making sure you know where to get. You can get online tutoring from Learning Resources. They have online tutors, even at like, it says 24/7 on tutor.com if the tutoring center tutors aren't there. But I've never tried to get a tutor at 2 in the morning. But you guys let me know how that goes. Face-to-face tutoring, tutor.com, group study, Zoom appointments with me, texting me at 2 a.m. to ask questions. That's funny, nobody wants to text me at 2 a.m. I appreciate that. You can text me other times. Email me, definitely email is good. Here's one. I'm planning to sleep on my textbook to learn via diffusion. We're gonna talk a little bit about osmosis at the end of this chapter, so that'll be pretty funny. Wait, hold on a second. Oh, I need to make it bigger. You guys are funny, so some of you just plan to sleep on your textbook. That's great. Actually, 40% of you guys. So for those of you who, you know, are trying to do a group study, you can actually use the chat right now to say, you know, I'm interested, and then maybe figure out how you can get each other's contact information, or basically just email. What I would also suggest is, you know, see, we have this discussion, you know, up on our course right now. You can use the course discussion side to see if anyone wants to start a group study. That's completely up to you guys, but you know, there are resources to do that. Oh yeah, I looked those up. Aren't they so cute? Discord server, we can help each other. Yeah, you guys could totally do that. So I'm glad you guys are doing that. Yeah, I love to do these things. I had a Japanese friend that every single text she sent, she would do these little cute, I guess, what do you call it? Like, I don't know what is the emoji thing, but I thought it was so cute. Okay, so I'm gonna go ahead and end polling. 2 of you again didn't vote. I don't know why, but maybe because your phone or something doesn't let you vote. I'm gonna go ahead and share the result, so you guys can take a look here. So if you guys were online and didn't get to watch this live, you can definitely take advantage of the discussion in the course content area to see if you can set up anything for a group study. All right, continue on after our poll. 17.2 grams of ethylene glycol. C2H6O2 in 0.500 kilograms of water is your solution, okay? And it says here, final volume. So when you take 17.2 grams of ethylene glycol, you mix it with 0.5 kilograms of water. The final volume of the solution, it ends up being 515 milliliters. Okay, I'm gonna go ahead and write down the molar mass of ethylene glycol too. So molar mass of C2H6O2 is 62.07 grams per moles. All right, so We have this. So if you guys want, maybe I can, let's see, post that link. Actually, you guys can probably post that link on discussion too, right? So go ahead and do that, okay? I can post that link too, just remind me, or send it to me so I can post it on the class on an announcement. And if one of you wants to like say like this is the group study we're doing, who's interested and stuff like that, okay? So anyway, so I have this 62.07 grams per moles here. All right, so A, we want to look for molarity. B, we want to look for molality. C, you want to look for percent mass. D, you want to look for mole fraction. E, you want to look for mole percent. So we're going to look for 5 things here, okay? So based on just 17.2 grams, 0.5 kg, 515 mil, and the molar mass, I want you. Thank you, Abiana. Is that how I say your name? Am I saying it wrong? Tell me if I'm pronouncing it wrong. Okay. Yay. Oh, I wanted to show you guys my shirt today, but it's a really, really funny shirt. While you guys are writing this, well, I guess you should write that. I'll give you guys a few seconds to write the question. But I have this shirt that says it's a cat ion shirt. It's like a dictionary pronunciation. It's really funny. All right, so molarity, molality, mass percent, mole fraction. Okay, so hopefully you guys had time to write it. Now, I'm gonna show you, let's work on molarity first. Any ideas on how to do the molarity? We need moles of solute, right? Divided by liters of the solution. Well, the liters of the solution part was pretty easy because it kind of gave it to us on the question already, right? 515 mils is 0.515 liters on the bottom. So I have that part from there, okay? All I gotta do is find the moles of solute. So I guess we'll go ahead and do that. How do you find the moles of solute? Well, the solute is ethylene glycol here. So we take 17.2 grams of ethylene glycol.
Can you move the camera down, please?
Do this, is that better?
Yeah, okay, I just couldn't see what you were writing. So thank you.
All right, ethylene glycol. 1 mole, I'm just gonna write G, is 62.07 grams. That will give me, so I'm gonna keep 3 sig figs here. So I'm gonna go ahead and write down extra number and underline that number I know I need to stop at. Right, so that's another thing you learn in Chem 1 where you just don't round until the end. Usually, I like to just write down extra numbers and underline where I'm supposed to stop, okay? So I'm gonna take that moles and put it up here. So 0.2771, but really it's 0.277 moles on the top. And then we wanna divide it by 0.515 liter. So you will get 0.538 molarity here. Okay, so very important to distinguish between your capital M and lowercase m. Like right here, okay? Now, because the next one, they're asking for molality. So remember, molality is the one that's not solution on the bottom, it's only solvent on the bottom. So it's moles of solute, which luckily for us, we already solved it. We can just plug that in. And kilograms of solvent. So our case, what is our solvent in our case here? So zoom out a little bit so you can see the question. It was 0.5 kilograms of water. So water was your solvent here, okay? So basically you need to put 0.5 kg of water down here. And on the top is 0.277. That should give us a molality here. So let's take a look and see what we get. The molality is 0.554. You notice the numbers for molality and molarity are pretty close usually. Okay. Any questions so far? Let me know if you have any questions, okay? So if not, I'm gonna go ahead and continue. We wanna do the third one. We wanna do percent mass. So if you remember from our chart earlier, percent mass, basically you take the mass ratio and then you multiply by 100 to get the percent. So the mass ratio is mass of your solute over mass of everybody, which is solute and solvent. Okay, and you take this, you times 100 to get percent. All right, so we have this times by percent, and then you go ahead and just plug in all the values. Let's see if we have everything, and we actually do. Mass of solute was given as 17.2 grams, right? That was on the question. And they also told us the mass of the solvent, it was 0.5 kilograms of water. Well, you gotta make sure your units are all the same. So since we're starting off with grams here, let's go ahead and turn 0.5 kilograms to grams. Can you guys do that? How many grams is that? 0.500 kilogram is?
500 grams.
It's 500. So I guess technically it's 366. You'd have to like do your period right there. Or you could write it in like scientific notation, but I'm just gonna do this for now. Right there on the bottom, okay? So that's the water, that's the solute, so solute and solvent on the bottom. And then you take that and times 100. So that should be pretty simple. Is 17.2 divided by 517.2 and then times 100. You should get 3.33%-ish. It's a very small amount of percent by mass. All right, let's go and do the next one. The next one, mole fraction. So mole fraction, we want to do just basically the same thing as the ratio over here, but in moles, okay? So mole fraction is that. So mole fraction will be moles of solute over moles of solute plus solvent. So you gotta do the moles of solvent too. So I guess you need the molar mass of water here. Do you guys know the molar mass of water? I'm gonna go ahead and write it out for you if you don't remember.
Is it 18.01?
Yeah, it's 0.1 something. It rounds out to 0.2, I think. That's awesome, really close. So you do this long enough. I think ammonia is like 17.03 or something like that. You just start remembering stuff you don't intend to remember. Okay, so water is right here. So we can get the moles of the solvent. Very good. So let's go ahead and do that. We already did the moles of solute. So I'm going to go ahead and write those down first. 27, not 22. Sorry. Oh, I'm messing up. I'm gonna erase this and start over. Two, seven, seven. And then I'll put the 2771 on the bottom. All right. What'd you guys get for the moles of water? It was 500 grams of water, right? And 1 mole was 18.02 grams. So you end up getting 27.75. 75, but really just keep 3 fixed right here. That's the mole of water right there. So I'm gonna go ahead and put that big 27 right here. So that will give me my mole fraction. So these two add up, and then you divide by top and the bottom. You end up getting 0.989%. Very small amount, I mean, because this is 0.27, this is 27 plus 0.27 over here. Okay? 27.747, yeah. Perfect. Yeah, I just kind of sort of rounded it, but I still kept one extra number. But you could have kept 747 and underlined the 7, same thing. All right, so now that we have mole fraction, the next one is mole percent. It's super easy. So to get mole percent, you literally take the mole fraction and you know what? I just did the wrong thing for you guys. That's so funny. That's the mole percent. I accidentally gave you the answer. I did 100. It's 100 less than that. So it's 9.89 times 10 to the minus 3. And there's no unit for fraction. This fraction is out of 1. It's going to be number smaller than 1. So that's that number right there. And you take, if you wanted to get mole percent, you take the mole fraction times 100. Okay? So you get that times 100, and then you get 0.989. Then I wrote the percent down because it's percentage. All right. Any questions on converting units right now? Hopefully everyone's good. Make sure you practice doing these problems again when you go back and take a look at your notes. Definitely you want to practice that a little bit. Now the next part here on our lecture, on our slides here, it talks about Raoult's law, which is a vapor pressure of solutions. I want to take a skip on that a little bit and tell you a little bit more about what we're doing in lab next week. Because it's kind of, that way when you do your pre-lab, you're not like, oh, what? Okay, so let me show you guys what we want to talk about. So the next lab that we have after safety is called the colligative property lab, which is really KF lab. Okay, so I wanted to show you guys, if you haven't seen this in Chem 1, because a lot of you have different teachers and some of your teachers don't. Some of teachers do that part, some don't even make it past Vesper. So hopefully you guys have heard of Vesper before. All right, I'm gonna go ahead and turn the page, okay? So hopefully you had enough time to write. Now, I want to talk about what we learned in the phase diagram. So hopefully you guys learned phase diagram in Chem 1 as well. Now, if you didn't, you wanna take a look at the notes I have set up for you guys. But one important thing about a phase diagram is when we started with the phase diagram, there was always like a few different curves. So I'm going to talk about the one for water right now, okay? So I'm going to go ahead and draw out a little graph that we can have here. So on this side here on the y-axis, we want to put pressure and we want to put temperature on the x-axis. The pressure can be ATM, torr, millimeters mercury, whatever, depending on the units, but I'm not really worried too much about that right now. And then we have temperature. Usually we use Kelvin or Celsius. Okay, so there's one first curve that we learn about is basically this line right here. This line basically talks about the vapor pressure, which was why we would go to the vapor pressure part. But basically, what in the world is the definition of vapor pressure? So we learned this before. Vapor pressure of any solution is basically if you leave a solution out in a closed system, over time, the molecules or the atoms in a solution will turn into gas. And at the same time, some of the gas form will turn back into a liquid. So there's vaporization and condensation happening at the same time. Okay, so this is in a closed system. So just imagine a little, maybe just a beaker of water. Okay, and then you put a watch glass on top of it. And then basically over time, there's some evaporation happening, and then there's some condensation happening. Now, when that condensation and evaporation gets into dynamic equilibrium, that means the rate of evaporation and rate of condensation is the same, there is a fixed amount of gas vapor, water vapor in the system. That vapor, the gas there, gives you the vapor pressure. Okay? Good luck with your test, Maria. You can check the rest after lecture. I have it recorded on a post-it. All right, I'll see you Monday, Maria. All right, so we have this here. This is a vapor pressure. So if you forgot what vapor pressure meant, it's basically when it hits equilibrium in a closed system, there's a gas amount. The more gas you have, the higher vapor pressure. Now, what makes there to be more gas here? If you increase the temperature, more of them will want to turn into gas form. So as you increase the temperature, the vapor pressure increases. So this is the line right here, right? So that's the vapor pressure curve. And from the vapor pressure curve, you guys learn to find the boiling point of whatever this liquid. So let's say this is water. We'll just say water. What is the boiling point of water, and what's the definition of boiling point? So this is something else you learn in Chem 1. The boiling point is actually just a definition. The boiling point is the temperature where your vapor pressure of the solution has now equal to the vapor pressure of the external condition. So if your outside surrounding is like 100 atm, then your vapor pressure needs to be 100 atm before it can boil. Okay? So do you guys need me to write that down? What the boiling point temperature definition is? Okay.
Yes, please.
Yes, please.
All right, so we have so the first definition, boiling point means temperature where vapor pressure of our solution, of our liquid, right, of the liquid, which is water in this case, equals, I guess you write equal the external, basically environment pressure. So that's what really boiling point means. And then you guys remember learning something called the normal boiling point? Remember that? So what in the world is boiling point and the normal boiling point? Go ahead and tell you guys here. Basically, because our atmosphere here, and we do a lot of our experiments under 1 atm, we basically assign 1 atm as our standard. So normal boiling point is the temperature where vapor pressure of the liquid equals the external temperature of external pressure, like that. of 1 atm. So that means your vapor pressure has to be 1 atm and your external pressure is 1 atm. That's normal boiling point. Any other pressure that's not 1 atm is just called boiling point. So you guys ever like have you heard like, you know, if you go like climb Mount Everest, like sometimes somewhere really high elevation, the water actually boils at a different temperature than 100 degrees. Because at 1 atm, our normal boiling point happens to be 100 degrees Celsius. Okay, if you go up to higher elevation, the external pressure is lower, so it'll actually boil at a lower temperature. I think Everest boils at like 78 point something Celsius instead of 100. So it's kind of cool, okay? Basically, because the atmospheric pressure when it's high elevation is a lot lower. So anyway, so that's the stuff where you learn boiling point and normal boiling point. That's from Chem 1. And you can find that on this curve here. So basically, every single dot on this line here represents a boiling point. You combine all of them here, all the temperatures, you get a curve. But specifically at 1 atm pressure, you will get the normal boiling point. And so for water, we know water boils at 100 degrees Celsius at 1 atm. Okay, so that's something we want to focus on here. I guess I could draw the 1 atm line here too. Let's say this is 1 atm. I'm just making it, it's not like to scale or anything. So like, don't like be comparing my drawing to some research article or textbook drawing. Say, hey, your picture doesn't match. It's because I'm free drawing it, okay? And I went to school for chemistry, not art, so I don't have the best art skills. You guys might have better art skills than I do though, so you could show off on your book and show me on your notes if you wanted to. I could post it if you have really cool pictures and stuff. All right, so we have this here now. If I have 1 atm, I drew this line across here, that point here should go down to 100 degrees Celsius because I know that's my normal boiling point for water, okay? So it's kind of cool. You can find boiling point or normal boiling point from the curve. If the pressure is less than 1 atm, you will get something lower. You see? Less than 1 atm, you get something lower than 100. Now, if you increase the pressure, then your boiling point increases. It's kind of cool how you can change stuff like that based on just messing with the pressure. Now, that's one line of the phase diagram. The other line of the phase diagram is the basically so this line here is division between the liquid and the gas, right? Because for it to cross from liquid to gas, it has to pass the boiling point. So the other line I want to draw for you guys here is going to be the line that separates the liquid from the solid. So basically, at this point here, at 1 atm, if you draw it down all the way down, that should be your normal freezing point, and that's 0. That's for water, okay? So, and then you have another line on your curve that separates, I kind of had to curve a little bit, solid and gas. And you guys remember we said, what's on this line? 2 phases exist at one time, liquid and gas. What's on this line? 2 phases exist at one time, solid and liquid. What's on this line? 2 phases exist at the same time. This is solid and gas. On this point here, that was called the triple point where all 3 phases exist in equilibrium. That is kind of cool. Like, have you ever thought about like trying to change the pressure and the temperature to get to this point and you can see what's in your flask? It would be pretty freaky because all 3 phases will exist somehow. Okay, now there's something else on the phase diagram that we learn when you go past a certain point up here where it's high enough pressure and temperature. So I guess we'll call it a critical point up here, where over here in this region above that, we have supercritical fluid. You guys remember learning that too? So that's supercritical fluid. It has to go past a certain temperature and pressure, which we call it the critical point. I guess I'll write on the bottom. Okay, so that red dot here, we'll call it critical point. All right, I'm gonna write down here, critical point. Basically, there's a critical pressure and temperature. And then above this, supercritical fluid exists. So supercritical fluid carbon dioxide is actually used to decaffeinate stuff, coffee, tea, you know, the natural, they call it the natural alternative decaffeinating using carbon dioxide. It's actually supercritical carbon dioxide. Kind of cool, okay? All right, so that's what we have for our phase diagram from, so if we needed to write it, from Chem 1. I could zoom it out so you can see the whole picture at the same time. Is that better? All right. So anyway, so that's for water. Now what I wanted to do was tell you something really cool about, since we're in the topic of solution. So water is just a solvent, agree? Water is just solvent. We are in a chapter called solutions. So obviously we're gonna have to talk about solutions. So what is a solution here? Solution of anything that's made of water is an aqueous solution. You can make all different kinds of aqueous solution. You can make sugar solution, you can make salt solutions, you can make different kinds of salt solutions, and you can make different concentrations of solutions, agreed? All you do is dump stuff into the water. So here's the idea here. Now, do you know why people put salt on the road when it's like cold? Why do like some states like dump, obviously it doesn't happen in Florida very much, but right, it prevents ice from forming. But how? Why? So it actually has to do with this, okay? So when you have a solution, because this is water here, anytime you have a solution, right, the freezing point will actually lower. I will show you this on this picture here, okay? So here's my colorful pen here. Hopefully they work. I'm testing them out. So let's say we make a solution by taking that water and putting some sugar in that water. So what happens to my phase diagram is it expands. Same water, you just made it into a solution by dumping some sugar in it. You just made it expand. When you expand that phase diagram, what happens to your freezing point? It just dropped. The more solute you put in there, and depending on what kinds of solute, if it's ionic solute, it multiplies the impact with the number of ions per compound. So it's really cool. The more, so let me draw another line and then we'll start labeling them, okay? It lowers the freezing point that way. So this is my purple pen, makes it even fatter. And then we'll find another color here. Oh, I have blue, I can do blue. Oh, I can do red too. I don't think I need that many lines though, huh? There should be enough of a illustration here. So these are all different kinds of solution based off water. So water is the black one, so I'll call this water. The first one maybe is 1 molality of sugar solution, okay? 1 molality of sugar. Now, if I do 1 molality of sugar, it just makes it that much wider, right? So the next one here, if I did 1 molality of NaCl salt, it actually is double the impact of sugar because NaCl splits 2 ways. The ion splits 2 ways, so it doubles the impact. So if what usually people do for the salt on the road is going to be CaCl2. It's even a bigger impact because there they have 3 ions, even though it's just 1 molality. So the higher the concentration, the bigger the split will be, the fatter it will get, so the lower the freezing point will be. And depending on what type of salt, or if you use a non-ionic compound, you can also predict how much it shifts. So there's going to be calculations involved in this, but yes, it does prevent ice from forming. So what they do is if they toss some salt on the road, that's CaCl2 here, you see how much it just lowered the freezing point? So when the water is on the road, it cannot refreeze until it hits the much lower freezing point. So that means you prevent black ice on the road, which makes it safer to drive, but you do need to go wash your car after that because you want salt on the car all the time. Okay, so that's the idea behind this. Your experiment is based on this concept here, KF lab. You're gonna basically check how much salt do I put in and what's the impact on my salt and how much does it lower the temperature. And based on that lowering temperature, you actually calculate a value of your constant that you already know. The constant that we are after here today is basically the freezing point depression constant. So freezing point always lowers with any solution that you have. Boiling point is interestingly going up. You guys notice how the boiling point is increasing? And then the freezing point is getting down. So they always tell you, put some salt in the water and makes your pasta boil faster, right? Doesn't people say that? So it's really just when you put salt in the water, technically you're increasing the boiling point. So it's boiling it hotter, so it should cook faster. Isn't that interesting? So you learn something new every day. Well, maybe you already learned that, but I like to tell people in case you guys don't. But so that's what we're gonna be doing in lab. Okay, so let me show you a calculation here. What we're gonna do. When we get back, I will teach you more in detail. We'll start comparing different kinds of solution. Actually, if we have time, I'll do that. But the calculation you need to have in lab is gonna be this. So basically, delta TF is the change in the temperature. So delta is change in your freezing point, okay? Change in your freezing point temperature equals to I, which is I is called the Van Hoff factor. So let me write that down. Van Hoff factor is basically how many ions it splits into. Okay, multiply with M. And what's M? Molality. Multiply by KF. And that's what you guys will be solving for. But KF is actually constant. You already know the answer. But you're just kind of seeing how close you can get to KF, basically. The experiment will be, okay? So KF is called the freezing point depression constant. And for water, so KF for water is 1.86 Celsius per molality. I think your lab wants you to do 1.856 or something like that, but 1.86 usually generally works. Okay, so what's I? I is how many ions it splits into if it's ionic. If it's not ionic, it doesn't split, just leave it as 1. There's no, basically it doesn't split. You don't even have to write it if it's not ionic. But if it's ionic, you better put it in there. Okay, so your job for your I, you guys, I think you'll be using sodium chloride, so your I will be 2 here because NaCl is 2 ions. And then molality, you'll have to somehow calculate your molality, which is moles of solute per kg of your water. And then you'll be able to solve for your KF. And then you'll compare how close your KF to 1.86. Okay, so that would be your calculation. Now, this here is very important. Is the absolute value, okay, of freezing point depression. So like basically, if your temperature was originally 0, agree, for water is 0, and it's gonna go down to like negative 3.1 maybe. What do you write on here? Do you write negative 3.1? No, I just go ahead and write, well, the difference between 0 and negative 3.1 is 3.1. So that's why I put the absolute value there. You just put the positive value on here. Okay, so you put 3.1 Celsius here, you put your I, and you put your molality, and you can solve for your KF that way. All right, so the same thing with boiling point. It's the same formula. Go ahead and use a different color. We'll use black. I'm gonna write on the next page because I don't have space on this page, okay? So same formula for delta TB. Boiling point elevation, that one here is, we can do, so if you start off at 100, so if you raise your temperature to 5, delta TB will be 5 degrees. I mean, raise the temperature by 5, so let's say 105 boiling point, your delta TB will be 5. 106 boiling point, your delta TB will be 6. Okay, so I just like to put the absolute value to remind you, but it's going to be positive, but sometimes I like to keep it consistent. The freezing point is what confuses people. They put a negative there and everything gets funny because they're all going to be absolute value here. So this one here is boiling point elevation. Okay, and then it equals to, again, I, M, and then KB. So it literally is like just the same formula. I is the Van Hoff factor, right? So how many ions it splits into, agree? This one is the molality again. And this one is the boiling point elevation constant. Now for water, the boiling point elevation, KB of water, is 0.512 Celsius per molality. So that will be what you guys will be using to calculate here. So based on this here, okay, I want to give you a scenario where I have A, I have pure water. B, I have 2 molality of sugar solution, so in aqueous, so this is aqueous because it's in water. And then I have option C, 1 molality of NaCl, aqueous. And in option D, I have 1 molality of CaCl2, aqueous. Okay, so I want to ask you, let's just say at 1 atm, A, B, C, or D, who has the lowest freezing point? What do you guys think? The lowest freezing point. So do you want to take a peek? Well, basically, you have to see how, this is the standard, the baseline, and then you have to see how much these guys get bigger and bigger, right? So how fat the graph expands. Let me show you right here. How fat this expands here, it depends on your I times your M. Agree? Because the temperature falls, so if you want to do delta TF is I times M times KF. Now, if everybody is aqueous, your KF is the same. So you don't have to worry about multiplying the KF. Unless you really wanted the exact number, you put your KF in. But if you're just kind of qualitatively judging it without actually calculating the number, you don't have to worry about a KF because they're all aqueous here. And you know this guy is 0. And everybody here is lower than 0 because it's freezing point depression. Okay, so what you can do is judge the I times the M to see how far the graphs go, how low it shifts it. So this guy here, sugar, KF, we don't have to worry. We could do KF on here, but everybody has the same KF, so you just be doing extra math. It doesn't matter. But what matters is the I is 1. Okay, so this is 0 here, 0 Celsius. And then this guy here, IM is, what's the I? Nothing, it's just 1, right? Because sugar doesn't split. So 1 times 2 molality. I'm just gonna go ahead and write the 2 there. So my IM factor here is 2. So it'll be 2 times the KF to get the actual temperature drop. But I don't really care about the temperature drop, I'm just wanting to know which one would be the lowest. If you did the KF, you could find the exact temperature that it drops to. This one here, IM, would be 2 ions. So 2 times 1 molality is 2. So these two would actually have about the same impact. Their freezing point would drop to about the same amount. So you couldn't tell, I mean, unless you did it, you know, maybe one is slightly different, but calculation-wise, it's the same, okay? Now, what about this one? This IM for part D is splits how many ways? CaCl2 splits 3 ions, okay? So 3 times 1, that's 3. So the lowest freezing point should be this guy because it goes the furthest, the fattest expansion. The bigger the expansion of the graph, the lower the freezing point will be. Agree? So the answer for the lowest freezing point will be D. Okay? Now, just kind of throw things out there. What about the highest freezing point? What do you guys think?
It'd be water, right?
It would be water. Now, if I took away water, you'd be like, well, it could be B or C, I don't know. But I put water in there, so you know water is the baseline. Highest freezing point will be A. Okay, now, let's go ahead and twist it around now. What about boiling point? Let's do the lowest boiling point. Which one would be the lowest boiling point? Now remember, it starts from water and it goes up from there. Agree? So which one has the lowest boiling point?
Water.
Water, very good. So that's A again. What about the highest boiling point?
CaCl2.
Very good. It would be CaCl2. So I just wanted you guys to know that sometimes there are questions that will ask you to just qualitatively do it. You don't want to spend all your time punching in numbers. You can just literally look at it and know which one's going to be lowest and highest. Okay, now if they ask you specifically to do the calculation and see what the exact number is, then yes, plug in the KF and then you do your math.